Right now, you're sitting somewhere. On a chair, on a bed, maybe on the floor. It feels solid, stable, reliable. You can put your full weight on it without even thinking. Your brain is confident this is real. But now, imagine a simple experiment. We start to zoom in. Inside the chair. Inside the wood. Inside the atoms. And suddenly, something strange happens. What felt completely solid a moment ago turns out to be almost empty. Mostly nothing. Zoom in even further. At the center of every atom, there's a tiny nucleus. Around it, particles that don't really move like planets, don't sit still like objects, and don't behave the way our intuition expects. Here, things don't exist in one clear state. They exist as possibilities. And only when we look do they decide what to be. And the deeper we look inside an atom, the less reality behaves like reality. Richard Feynman once warned us about this. He said that nature is not classical. It doesn't follow the rules of common sense. What we experience every day is just the surface layer of reality. The real story is happening underneath. So the question is, if reality is this strange at its core, why does the world feel so normal? Let's begin there. Pick up any object near you. Your phone, a book, even your own hand. It feels solid, heavy, real. Now here's the uncomfortable truth. That object is not really solid. Let's zoom in again more slowly. Inside your hand, there are cells. Inside cells, there are molecules. Inside molecules, there are atoms. And inside an atom, there is mostly nothing. To understand this, imagine a massive football stadium, the kind that holds tens of thousands of people. Now place a single ant at the exact center of the field. That ant is the nucleus. Everything else, the seats, the air, the space, that's where the electrons might be. The rest is empty space. So naturally, a question should hit you right now. If everything is mostly empty, why don't you fall through the chair? Why doesn't your hand pass through the table? This is where reality quietly surprises us. The solidity you feel is not because atoms are tightly packed like bricks. It's because of forces, invisible forces. When your hand touches the table, the atoms in your hand never actually touch the atoms in the table. What happens instead is a powerful electrical repulsion, like two strong magnets pushing against each other, but at a level too small for your eyes to see. Your brain translates this invisible resistance into a simple feeling, solid. Here's the strange part. What you experience as hardness, weight, and texture is not matter touching matter. It's force talking to force. This isn't a theory sitting in a textbook. If this repulsion didn't exist, you would fall straight through the floor. Buildings wouldn't stand. Your body wouldn't hold its shape. Every solid object around you is standing on invisible rules you never notice. And once you realize this, the world doesn't feel fake. But it doesn't feel as simple as it used to either, because solidity isn't what it looks like. It's an illusion created by deeper laws of nature. And this is just the first layer. As we go further inside the atom, even the idea of things begins to dissolve. When most of us first learned about atoms, we were shown a simple picture, a tiny solar system, a nucleus in the center, and electrons neatly orbiting around it like planets. It feels comfortable, familiar. Our brain likes it because it matches something we already understand. But that picture is wrong, not slightly wrong, completely wrong. If electrons really moved like planets, atoms wouldn't even survive. They would collapse in a fraction of a second. So what are electrons actually doing? Imagine a ceiling fan in a dark room. When the fan is off, you can clearly see the blades. But when it spins fast, the blades disappear. All you see is a soft, blurry circle. Now here's the key shift. That blur is not a thing. It's not a blade. It's a pattern of possibility. Electrons behave in a similar way. They are not tiny balls racing around the nucleus. They don't follow clean paths. They don't have exact locations waiting to be discovered. Instead, they exist as a kind of cloud. A probability cloud. It tells us where an electron is likely to be, not where it is. This feels deeply uncomfortable at first, because our everyday world doesn't work like this. A car is either in the parking lot or it isn't. Your phone is either on the table or in your hand. But inside an atom, nature refuses to give us that certainty. An electron doesn't say, "I am here." It says, "If you look, you'll probably find me somewhere around here." And the moment you try to pin it down, the whole picture changes. This strange idea isn't philosophy. It's been tested again and again in laboratories. It explains why atoms are stable, why chemistry works, why matter doesn't collapse into nothing. Here's the quiet truth hidden inside all this. Inside atoms, particles don't behave like objects. They behave like possibilities. And once reality starts acting like possibility instead of certainty, we're no longer dealing with the world we grew up believing in, because the next question becomes unavoidable. What happens when we look at these possibilities? That's where things get even stranger. Now pause for a second. So far, atoms are already strange. Electrons are not little balls. They're clouds of possibility. But here's where reality really starts to slip. Electrons don't just behave strangely. They actively change their behavior depending on whether we are watching them. This isn't a metaphor. This is something physicists have tested in real experiments. Imagine a person alone in a room. Relaxed, natural, unfiltered. Now imagine the same person suddenly realizes there's a camera on them. Their posture changes. Their movements change. Their behavior is no longer the same. Inside the quantum world, particles do something eerily similar. When we don't look at electrons, they spread out like waves. They interfere with themselves. They act as if they are everywhere at once. But the moment we try to observe them, they snap into a single position, like a particle, wave, or particle. The strange part is they are not switching between two modes we choose. They follow rules that don't exist in our everyday world. Here's the famous experiment that revealed this. Electrons are fired one by one toward a screen with two tiny slits. If electrons were particles, they should form two neat piles behind the slits. But they don't. They form a wave pattern. Even when electrons are sent one at a time, it's as if each electron is somehow interfering with itself. But the moment scientists place a detector to check which slit the electron passes through, the wave pattern disappears. The electron behaves like a particle again. Just because we looked, this is the moment where amazement turns into unease, because this means something profound. Reality is not fully defined until it is observed. The act of measurement is not passive. It's not like taking a photograph. It's more like asking a question that forces nature to answer. And nature answers differently depending on the question. This is why physicists stopped asking, "What is an electron really?" and started asking, "What can an electron do when we interact with it?" Because in the quantum world, observation is not outside the system. It's part of the system. And once you accept that, you can't help but wonder, if observation changes electrons, what else does it change? That question takes us straight to a humbling realization made by one of the greatest physicists who ever lived. At this point, a natural reaction kicks in. Okay, this is getting too weird. Surely by now, physicists must understand what's really going on. That's when Richard Feynman steps in and quietly pulls the rug from under our feet. Feynman, one of the greatest physicists of the 20th century, once said something that still makes scientists uncomfortable. No one understands quantum mechanics. Not beginners. Not experts. Not even the people who built the theory. At first, this sounds shocking. Almost irresponsible. How can a theory be so successful? So accurate, and yet not truly understood? Think of it like this. You can drive a car every day. You know how to steer, brake, and accelerate. You trust it with your life. But if someone suddenly asks you to explain how thousands of explosions per minute inside the engine turn into smooth motion, most of us go silent. The car works perfectly, even if the deep details remain a mystery. Quantum mechanics is like that, but at the scale of reality itself. Physicists know the rules. They know how to calculate outcomes with incredible precision. In fact, quantum theory is the most accurate theory humans have ever created. It predicts experimental results to many decimal places. No guessing. No luck. And yet, when we ask the deeper question, what is actually happening? The theory goes quiet. There is no clear picture. No story that feels intuitive. Just equations that work. Feynman's point wasn't that quantum mechanics is broken. It was that our intuition is broken. We evolved to understand stones, trees, and moving animals. Not atoms. Not probability waves. Not realities that change when observed. Here's the humbling truth hidden inside Feynman's statement. Nature doesn't owe us understanding. It only owes consistency. And somehow quantum mechanics delivers that consistency flawlessly, even while refusing to make sense in our everyday language. Once you accept this, confusion slowly turns into wonder, because it means reality is deeper than our imagination, not shallower. And if the universe runs on rules we can use, but not fully visualize, then the next question becomes inevitable. What exactly is the universe calculating underneath everything we see? That question leads us to the strange idea that probability itself may be running the cosmos. By now, one thing is becoming clear. The universe does not like certainty, at least, not at the deepest level. In our everyday life, we expect precision. You throw a ball, you know where it will land. You set an alarm, you know when it will ring. Cause effect, predictable. But inside an atom, nature plays a different game. Physicists can't tell you exactly where an electron is. Not because our tools are bad, not because we haven't tried hard enough, but because the universe itself refuses to decide. Instead of giving exact answers, nature offers probabilities. This doesn't mean chaos. It means a different kind of order. Think about a weather forecast. You can't say, at exactly 3:17 p.m. one raindrop will fall on this street. But you can say, there is an 80% chance of rain today. And most of the time, that prediction is surprisingly reliable. Quantum physics works the same way. It doesn't predict what will happen. It predicts what is likely to happen. And when you repeat an experiment thousands of times, the results line up perfectly with those probabilities. That's the intellectual shift. Uncertainty is not a flaw in the theory. It is a feature of reality. There's even a hard limit built into nature itself. A rule that says you cannot know everything at once. You can't know a particle's exact position and its exact motion at the same time, not because you're careless, but because reality doesn't allow it. This is where many people feel uncomfortable. If the universe runs on probabilities, does that mean reality is random? No, it means reality is statistical. Over large numbers, the universe is incredibly stable. That's why atoms form. That's why chemistry works. That's why your body holds together. But at the smallest scale, nature leaves room for uncertainty. Here's the quiet truth hiding in all this. Nature doesn't promise certainty. It promises likelihood. And somehow, from that uncertainty, everything solid, stable, and predictable emerges. But there's one last twist. Because probabilities alone don't explain everything, there's still the strange role of the observer, the one who asked the question in the first place. And that changes everything again. Up to now, we could still pretend that reality is doing its own thing, and we are just watching from the outside. But this is where that comfort disappears. Because in the quantum world, you don't get to be a silent observer. Imagine asking someone a deeply personal question. The moment you ask it, their face changes. Their body language shifts. They are no longer the same person they were 1 second ago. Not because they were hiding something, but because the act of asking changed the situation. Inside an atom, measurement works in a strangely similar way. To observe a particle, you have to interact with it. You have to shine light on it, or place a detector in its path. And that interaction is not gentle. At the atomic scale, even the smallest probe is like a hammer. So when we say looking, we don't mean just watching. We mean touching reality. And the moment we touch it, it responds. This is why particles behave differently, depending on what we choose to measure. If you measure position, you destroy information about motion. If you measure motion, you lose certainty about position. Reality rearranges itself to answer the question you asked. This is the part that feels shocking, because it means outcomes are not pre-written. They are shaped in the moment of interaction. The observer is not separate from the experiment. The observer is part of it. This doesn't mean human consciousness is magically controlling the universe. It means that at the deepest level, there is no clean boundary between system and observer. Every measurement is a relationship. And here's the powerful realization hiding underneath. You cannot describe reality without including how you interact with it. Once you see this, physics quietly turns philosophical. Because if even electrons don't have properties until they are measured, then what does it really mean? For something to exist? That question brings us back to the everyday world, to our phones, computers, and technology, and reveals something even more surprising. This strange behavior isn't just abstract. It's the reason the modern world works at all. By now, all of this might feel very abstract. Waves, probabilities, observers shaping reality. It's natural to ask, why should I care? Because this strange, invisible behavior is quietly running your life. Right now, think of quantum mechanics like an operating system. You never see it. You don't interact with it directly, but without it, nothing works. Your phone screen lights up because electrons behave like waves. Transistors switch on and off because electrons can exist in controlled probabilities. Lasers work because atoms follow quantum rules, not classical ones. Every GPS signal depends on quantum physics. Every computer chip, every medical scanner, even the electricity flowing through wires. If atoms behaved like tiny solar systems, modern technology would simply not exist. This isn't accidental. Engineers don't need to understand quantum mechanics. In a philosophical sense, they need to know how to use its rules. And those rules work with terrifying precision. The same theory that refuses to explain what reality is can predict experimental outcomes better than any other theory humans have ever made. That contrast is humbling. The universe doesn't care whether our brains find something intuitive. It only cares whether the rules are followed. And here's where awe replaces confusion. From uncertainty, we built certainty. From probability, we built reliability. From something that doesn't feel real, we built the most real machines in human history. This means the world you touch every day is shaped by a layer of reality you will never directly see. A layer where things are not solid, not definite, and not independent of observation. And once you truly absorb that, the chair you're sitting on feels just a little bit different, because the most unreal-looking ideas are holding the real world together. So let's take a step back and look at what we've really uncovered. We started with something ordinary, a chair, a hand, a solid world we trust without thinking, and layer by layer that certainty dissolved. Solidity turned out to be mostly empty space. Particles stopped behaving like objects and started behaving like chances. Waves appeared where particles were supposed to be. Observation stopped being neutral and became part of the story itself. And somewhere along the way, we realized something humbling. Reality doesn't run on common sense. It runs on rules that work perfectly, even when they refuse to feel intuitive. Richard Feynman was right. The deeper we look, the less the universe explains itself in human language. And yet, from that strangeness comes everything. Matter, chemistry, life, technology, and you. What feels stable is built on uncertainty. What feels solid is held together by invisible relationships. What feels obvious is supported by ideas that sound impossible. Maybe the biggest lesson here isn't about atoms at all. Maybe it's this. Reality is not obligated to match how we imagine it. It only needs to be consistent. And once you accept that, the universe stops feeling broken and starts feeling far more interesting. So here's a question to sit with. If the deepest layer of reality only becomes real when it's observed, then what does that say about the role we play in the universe? I'd love to hear what you think.